Alrighty, solubility 3.10. So, first thing you need to remember from before is for molecular compounds, if you have bigger compounds, aka more molar mass, then you have a more polarizable electron cloud. And since you have a more polarizable electron cloud, you'll have stronger IMFs. So, when we're looking at these different compounds, we see this one is C2H6 and then C3, C4, and then C whatever. And so this one here that I'm circling is going to have less IMFs or not as strong IMFs compared to this one down here because of that polarizable electron cloud. So again, as a reminder, polarizable electron cloud means the electrons can move around, and so when they move around and if there's more electrons in this cloud, then you can have stronger partial charges. Alrighty, so these are solubility rules you need to be able to use, not memorize. They can be helpful to know if you want to, but you don't have to. There are some patterns to it if you did want to memorize it, but again, you don't have to. There is something you will need to memorize from 4.7, as I state right here, but I'm not expecting you to memorize it yet. I'm going to give it to you anyway in case you do want to memorize it, because this is the one rule right here that I'm pointing at that you do need to know. But otherwise, we'll talk about them more later. And so you need to look at this chart and be able to use it, or any other chart. This is just a random chart I found online. And so as a reminder, what is even solubility, or what's soluble? Soluble means it dissolves in solution. And so anything that's always soluble is going to always be able to dissolve if it has this ion. So for example, lithium cation, if I had something like lithium chloride or lithium hydroxide or something, those salts will always be soluble. And notice here it says based on water being the solvent, so we're talking about these in terms of dissolving in aqueous solutions. So you need to be able to use this or any other chart that's similar to this. Again, this is just a random one. Insoluble means that it is going to be not dissolved in water, and so it will be a precipitate or a solid if it is one of the products made in a reaction, or it doesn't dissolve if you start with that salt. So again, you have that chart, great. So what you need to do is, for these problems, practice using these rules, and then pause this video, try this your turn using the chart, and then notice I crossed out 6 and 7 because I realized this chart is a little incomplete, so it doesn't have the ability to do these two, but otherwise you could do the rest. So go ahead and try this out. And then I will show you the answers. Boop, boop. Here you go. Number 2 is tricky because if I look at sulfate here, sulfate is SO4 2 minus, and so this mercury is +2, versus this one says it's insoluble if it's Hg2 2 plus. So that means each Hg is 1 plus. They have to exist as Hg2, which is why it's together as 2 plus, and so that one might be tricky. Otherwise, the rest are fine. Coolio. Alrighty, saturation point. So the saturation point is the point where if I add a solute, some kind of salt or whatever, you could be dissolved in that solvent. Again, the solvent is usually water, and then you reach a point where no more can dissolve in it. So you add this salt or you add this solid, whatever that solid is, you're dissolving that in solvent, usually water, and then eventually you cannot add any more. So that's what saturation point is. Okay. There's a couple things it depends on. It depends on temperature and what solvent you're using, and of course the solute itself. Higher temperatures, usually more can be dissolved if I am at a higher temperature. You could see that in this chart here. So for example, sodium nitrate, if I'm at 0 degrees, I can do 70 grams of salt in 100 grams of water. And then as I increase that temperature, because temperature is down on the x-axis, notice I can add more. And so you could see that's for all of the cases, almost, except this one. But usually it's more. And so think about why that is. Normally this is talk to your neighbor, but I'm recording this. So think about it for a second and then I'll give you a reason. Alrighty. So why does temperature usually increase solubility, or the ability for some of these solutes to dissolve more? And so, as a reminder, temperature is related to kinetic energy. So if I am heating up that solvent, again, usually this is water, then I am giving the water molecules more kinetic energy. And so since we have more kinetic energy, that means we have the increased motion of the molecules. And so those molecules can collide with the solute more. So there's more frequency of it getting hit by the solvent. And so since that occurs, you can have more force in order for those collisions to happen. And so with more collisions happening with more force, then that can increase the rate that solute dissolves. And so, pretty common sense stuff. Just molecules hitting each other more. It's going faster, potentially. So, there we go. Alrighty. So, if you need the full definition of solubility, here it is. So, the amount of solute to form saturated solutions at some temp. So saturated means you are dissolving the solute and forming this solution. And then once you reach the, point that you reach saturation, then you reach that saturation point. It is very dependent on temperature, just as we explained the last slide. So there we go. So here's the definition of saturated. So it's a solution that has the exact amount of solute that can dissolve. Okay? Now, one thing for saturated is if I increase that temperature of that solvent, right? That means I can dissolve more. If I dissolve more, that's going to be called super saturated. Okay. All right. So, we talked about the word miscible. It means mixable, right? So, being able to mix with each other, or dissolve with each other, or be soluble with each other. So if they have similar IMFs, they tend to be more miscible in each other. And so, what the heck does that mean? So we have polar stuff versus non-polar stuff. And so, just as a quick reminder in your head, if you have something that's polar, that means you can dissolve something that is also polar. So if something has hydrogen bonds, for example, and I try to make it mix or dissolve in something else that also has hydrogen bonds or also has DDIs, like other kinds of DDIs, they're more likely to be able to mix with each other. They're more likely to be able to dissolve with one another. If I have stuff that's in general nonpolar, then it's going to dissolve in nonpolar stuff. So like dissolves like. That's a very famous phrase you might hear in other recordings of videos for stuff like this. Alrighty. Ionic versus regular molecular compounds. So if you think about IMF stuff, ionic has full charge versus molecular compounds that are polar are partial charges. So ionic stuff tends to dissolve in things that are more polar. So that's why water is good at dissolving salts that are ionic. And so if I add, for example, sodium chloride into water, well, that's ionic, so it's easy to dissolve in water. Leo. So like I said, like dissolves like, so polar dissolves polar, non-polar dissolves polar. Do not use that as an answer. in an FRQ or anything. Never. It's not explaining enough. You have to explain IMFs. You have to explain interactions. The like dissolves like is just an easy way to remember it, but you need to know why that occurs. So talk about IMFs, or if it's ionic, talk about, the ion to the hydrogen bond or whatever. Just make sure to describe why. Alrighty. So here is a saturated solution. So, or not yet. If I add 30 grams of sodium chloride to water, I'll get an unsaturated solution. There's a point that means I can add some more salt to it. Now, if I add 40 grams to it, then I have a saturated solution. It goes up to 36. There's ways to figure that out, but you don't need to know. So we'll just say, hey, look, there's 36. And then we have 4 grams left over. That is not going to be dissolved naturally in the water. Now, if I were to heat this up, I can dissolve that 4 grams eventually, depending on what temperature it needs to be at, and then it becomes a super saturated solution. So, like I said earlier, heating up solution more, I can add more solute. If I slowly cool it down, eventually I can get it super saturated. So that temperature, if I increased it to 50 degrees Celsius for that previous example, and I dissolve that part, eventually it could cool down to room temp and it's super saturated. It is not very stable. So here's an example here. I don't remember what compound this is, but if you slightly agitate it by just tapping it a little bit, then you start getting crystallization. So it's not hardcore stable once you've reached the point of being super saturated. All right. Concepts affecting solubility. So polarity, we just talked about that earlier. Like dissolves like. Again, don't use it as an answer. Make sure to talk about IMFs or whatever interactions there are. So cool. Pressure can affect solubility. So this is obviously related to gases. Liquids are not, succumbing to pressure in the ways that gases are, because liquids have a certain volume and then that's it. Gases can take up the space of any container, which is why we can put pressure on it. So if pressure increases, my solubility of the gas also increases. Now, one good example of this is, not that specifically, but pressure in terms of gas is soda. So soda has carbon dioxide in it. And so if in the cans, when you open one of those soda cans, you hear a little pop sound. And so the reason why is because they increase that pressure in that can, so the carbon dioxide remains dissolved in the soda. And so as you have that can open, you have now decreased the pressure. And so over time, your soda becomes flat because the pressure decreased, and so your solubility of carbon dioxide decreases, hence why the CO2 is slowly coming out of that soda. And so eventually you have flat soda because just over time, if your pressure had decreased, so your solubility of that carbon dioxide decreased. And so that's why that happens. All right, temperature affects solubility. We just talked about that earlier. And so it's pretty obvious with solids and liquids that temperature increases, solubility increases. What's weird is for gases, it's the opposite. Yeah. Now, the reason why gases are opposite is something that we'll learn. Oh gosh, I don't remember what unit. Unit 9? 8? I'm not sure. So we'll learn about that later. For now, just know that gases are opposite. There's something about heat energy and an equation for that. So that's why I'm not going to go over it. It's just the opposite. Okay, cool. That's it. Bye.